and geometric multiplicity. So regarding the, so we have to give a definition, which is algebraic multiplicity. So a given eigenvalue, lambda 0, so a single eigenvalue of matrix A, we know that it belongs to matrix A. This has algebraic multiplicity. Let's call this one AM, algebraic multiplicity. So a given eigenvalue, lambda 0, has algebraic multiplicity k equal to k. Okay, k is a number. If k is the largest integer, if k is the largest integer such that lambda minus lambda 0 to the power k is a factor of characteristic polynomial, is a factor of characteristic polynomial. Okay, so let me write here Pn in lambda. So this is what we denote in our class together, the characteristic polynomial. A matrix which is n by n, it should be of nth order in the unknown specific value. Now this is the algebraic multiplicity. Now we give another definition, which is regarding the geometric multiplicity. And the geometric multiplicity, we call this one the GM, or General Motors. Now, geometric multiplicity, GM, of a single lambda 0, so not all of them, but let's say each specific eigenvalue of a certain single lambda 0 is the dimension of the eigenspace, is the dimension of eigenspace. Or we can say that this is the dimension of the null space of, or this is the dimension dim of the null space of the matrix A minus lambda 0 I. This is the geometric multiplicity. So traditionally, if we get one eigenvector for each eigenvalue, we can denote the dimension of the geometric multiplicity. So far, we've seen that it is equal to 1. But it could be the case when each one eigenvalue can correspond to two different eigenvectors. At this moment, we consider that the geometric multiplicity of a single eigenvalue can have two eigenvectors which correspond to that. Now let's try to see an example, which would be, let's have a look. So given a matrix as in the board, which is 3, 0, 1, minus 1, 2, minus 1, 1, 0, 3. So let's have this matrix, and what you can do is that I can offer this here just so that you can follow my directions and solve this one on your own. So you can define the matrix A using a programming language. We can write it like this. You can, especially if you use Octave or MATLAB. This would be 3. You leave a space, minus 1, 1, semicolon, 0 to 0, semicolon, 1, minus 1, 3. So this would be the matrix A. Then you can say P is equal to the poly of A. Okay. Then eigenvalues. You can write here eigenvalues. This will be equal to the roots of P, okay? Which means that You first enter the matrix, then you find the characteristic polynomial, and this characteristic polynomial, it will give to you the major coefficients of all of the terms. So it's going to give the coefficients of lambda to the power 3, coefficients of lambda squared, the coefficients of lambda to the power 1, and coefficients of lambda to the power 0. But now, let's continue with this system. We have to find the determinant equal to 0 for this matrix. 3 minus lambda minus 1, 1. 0, 2 minus lambda, 0. And 1 minus 1, 3 minus lambda. So this is the determinant that we need to equal to 0. Now, it might be a good choice to find the determinant of this matrix by expanding it along the second row, because we have two zeros, okay? We have two zeros over there. And regarding this, we do this plus, minus, plus. So determinant, it will be equal to 2 minus lambda times 3 minus lambda squared, 3 minus lambda squared. Yeah, I was looking at this matrix, and I was trying to identify whether this is a symmetric matrix, but apparently it is not symmetric. A symmetric matrix is a matrix where Aij is equal to Aj. This would be a symmetric, but in this case, I don't see this, so it's not symmetric. Okay, now that we identified that, let's come back to the problem. And here we have the determinant of this matrix is 2 minus lambda times 3 minus lambda squared minus 1. This is equal to 0. Then let's move it again. So this is 9 minus, what is this? Minus 6 lambda plus lambda squared minus 1 times 2 minus lambda. And let's see if we can factor out this term. We get plus lambda squared is this. This is lambda squared minus 6 lambda plus 8. Here we have this. Can we factor out the lambda minus 6 lambda plus 8? This can be expanded as lambda minus 2 times lambda minus 4. Okay? So this is how we can factor out the second term. And we multiply this one also with minus 1 times lambda minus 2. And this would be equal to 0. So it looks like the characteristic polynomial of this matrix A, which is given at the top of the board, is equal to this expression. So in this expression, it looks like lambda minus 2 is a factor which appears twice, and we can again write that this is P3 in lambda. This is equal to lambda minus 2 squared times lambda minus 4. This is equal to 0. It looks like, what are the roots here? We expect to have 3 roots, and we can say that lambda 1 is equal to 2, lambda 2 is equal to 2, it's a double root, let's see it like that for a moment, and lambda 3 is equal to 4. Now, we need to, so we found 2 matrices. Now, what is the algebraic multiplicity of lambda 1 equal to 2? Algebraic multiplicity of this lambda, this is equal to 2, and the algebraic multiplicity of this lambda is equal to 1, because based on this definition. So if a root is to the power, if we have lambda minus x, lambda minus lambda 0 to the power k, that means that the algebraic multiplicity is k. Here we have that to the power 2 and to the power 1. So we can easily determine the respective algebraic multiplicities of all of the lambdas that we have in this for this specific matrix. Okay, so now the next step is that we need to define, or we need to find the eigenvectors. So first, let's try to see what is the what is the eigenvectors which are related to lambda equal to 2. So when lambda is equal to 2, what we write is the following. We say that this we have to write as ax is equal to lambda x. Right? This was the eigenvalue equation, and and then this would be then equal to ax. This is a vector. This is equal to 2 times x, where x is again a vector. And the question at this stage, now that we know what is x, the question is to find, once we know that what is lambda, this is the question, right? Then how do we solve this one? We look at the system, we say 3 minus 1, 1, 0, 2, 0, 1 minus 1, 3. This one times ABC, so the eigenvector, it should be 3 by 1. This is equal to 2 times ABC. This is equal to 2 times ABC. So this is equal to 2 times A, 2 times B, and 2 times C. So then, what are the equations that we can obtain from here? In fact, we can so this is one way to write them down, but probably a useful technique, it can also be observed like this. So we can have, let's have A minus lambda I, and this A minus lambda I, this would be equal to 3 minus 2, this is 1, minus 1, 1. Then here we have 0, 0, 0. And here we have 1, minus 1, 1. Okay, times ABC. This is equal to 0, 0, 0. So this is clearly that we're trying to obtain the null space of A minus lambda I, because we know that we are looking for this. We are looking for a vector x, which is the eigenvector, and it is in the null space of this expression. When we look at for the matrix in this case, we try to obtain the reduced row echelon form. And what is the reduced row echelon form of this expression? We have row 1, it has a pivot element of 1. So what operation can we do next? Next,
row
we can do the row 1. Yeah. Row 3 minus row 1. So in this case, it looks like, what is the rank of this matrix? What is rank of A minus lambda I?
1.
That is true. This is 1 because we have only one row which is independent. The other two, they are dependent. And so this is 1. And then, so allow me to write this one immediately 0, 0, 0. So we have two free variables. And the free variables, we can say that B, this number B is equal to S, and C is equal to T. So these are a couple of free variables. So if the free variables are 2, then what is the nullity? What is the nullity of A minus lambda I?
2.
2.
It's 2, because the null space of this matrix, it is composed of two linearly independent vectors. So the nullity is equal to 3. Then we have the rank nullity theorem. And the rank nullity theorem, it states that the rank plus the nullity, it should be equal to 3. Okay? And if you remember, have you seen the homework? Have you seen the homework you have due next Monday?
Yes, we have.
Yes.
Yes. Yes.
Without going too much into details, there is a question over there, which is question 7.6. In 7.6, there is a discussion of the null space of one linear transformation is the range of another linear transformation, T and S, etc. So when you try to solve that problem, try to think in terms of this rank nullity theorem. So we have a linear transformation. The rank nullity theorem it holds both for matrices and for linear transformations. So you can have a look at how these numbers play around when you try to answer that specific question. So this was equation or problem 7.6, just as a small hint and as a small reminder. Now let's come back here. So then it looks like regarding the expressions that we have here in the board, we can say that the unknown vector, so we have here A minus B plus C, this is going to be equal to 0. And this means that A, so this is the first expression. The second expression is B is equal to S. The third expression, sorry, C, because we have ABC, this is equal to T. And we know that C and T, they are any real number, so it's a constant. No, sorry, we said S and T. Sorry, let's do it like this. S is any real number, which means that this can be anything from minus infinity to 2 plus infinity, including the 0, right? And the T is also a real number, which might include any number from minus infinity to plus infinity, including the 0. So how do we write the first equation? So this is the only equation we can get from the matrix, right? We cannot get any more. Then we insert here the free variables, and then we obtain the following. We say that A, this is equal to B, which is S minus T. B is equal to S, C is equal to T. So then the vector ABC, this is equal to S times what? S times some numbers plus T times some other numbers. A is equal to 1 minus 1, B is 1, 0, and C is 0, 1. So this is the, let's say, the null space of the lambda minus 2i. So then we can say that the geometric multiplicity, the GM, geometric multiplicity of lambda is equal to 2 is equal to what? The geometric multiplicity is 2. So if we see here, the lambda equal to 2, it had the algebraic multiplicity equal to 2 and geometric multiplicity equal to 2. That's good. Now, so we solve this one, and whenever we're trying to find the basis which is going to diagonalize this matrix, we are going to use these two vectors as a basis, okay? Now, we need to find also what is the eigenvector which corresponds to lambda 3 equal to 4. For lambda 3 equal to 4, we can have a look here. So instead of this lambda, imagine what happens if we put here 4. So what will the matrix be then? The matrix will be equal to, here we have 3 minus 4, it's minus 1. Minus 1, 1, 0, 2 minus 4. What is 2 minus 4? This is minus 2. This is 0. We have 1. Minus 1. 3 minus 4. This is also minus 1. So, as a reminder, this is just A minus 4I. I is the identity matrix. A is what it is. So, this is what we finally obtain. And from here, we have this expression. And do we have anything that, so what is the rank of this matrix? We have to get the reduced row echelon form of this matrix, and then for sure the rank, it cannot be equal to 3, okay? Because we know that the determinant of this one is 0, so the rank should be at least 2. We don't know if it is 1, but if the rank of this one is equal to 2, what will be the nullity? Who can answer this? So let's take away this information. let's take away this one for a few moments, because this was just how you can use this in the specific programming language to find in an easier way the respective characteristic polynomial and eigenvalues. So we have here a 3 by 3 matrix, and the first option is for the rank equal to 3. Now this is not true because the determinant of this matrix is 0, which implies that the rank cannot be 3 but can be 2. If the rank is equal to 2, what is the nullity?
1.
That's true. The nullity would be equal to 1 because we know that the rank nullity theorem, it states that if we add those two together, we should get equal to 3. Now, this is the first option. Another option is the following. The rank here can be equal to 1. If the rank is equal to 1, what would be the nullity? The nullity would be equal to 2. So we don't know which one of these two options can come up. So let's try to obtain the reduced row echelon form of this matrix. So let's have this one, and let's multiply it by -1 the first row. We get here 1, 1, -1, and 1, 1, -1. We can divide the second one by -2. We get 0, 1, 0. And here we can have here 1, -1, -1. Then let's add, or let's do row 3 minus row 1. So let's do here row 3 star is equal to row 3 minus row 1. And from here we obtain 1, 1, -1, 0, 1, 0. And then 1 -1, 0. This is -2. And this is also 0. If this is 0, then the next step is we say that row 3 star is equal to row 3 plus 2 row 2. If we do this, then I believe you can see this part. Yes, you do. So then the next step, this is 1, 1, -1. This is 0, 1, 0. This is 0, 0, 1. One further step is that we can try to make this other number equal to 0. Sorry, this is 0.
Professor, for the reduced row echelon form, I got -1, -1, 1, 0, -2, 0, and 0, 0, 0, and the rank of the matrix 2.
Okay, that's true, but this is also true. So, so from this stage, we can subtract from the first one the second one. So the reduced row echelon form of this matrix, it looks like this. Can you compare your reduced row with this one? What do you obtain?
I got the same.
They are the same. Okay, that's good. So probably the one that is on the board is a more simplified version. So this is the, let's not forget, we're trying to get the reduced row echelon form of this one. So then let's try this again. This is 1, 0, -1, 0, 1, 0. And here we have 0, 0, 0 times the unknown vector ABC. This should be equal to 0. So we are looking for the null space. And then if we try the way that, so this is everything which is below the red line is equal to 0. The leading ones, they are located in here. So we have only one free variable. So we can say here that C is equal to any variable S. So S is a number from -infinity to +infinity, which makes it any real number. And then, so from the first equation, we get that A minus C is 0. From the second equation, what do we get from the second equation? P is equal to 0. And the third equation is that the third value C is a free variable S. Okay. So these are the three equations. The first one is, what is this one? This is wrong. This is A. Okay, sorry. Because this is A minus C. Then here we get A is equal to S, P is equal to 0, and C is equal to S again. Yes. So this implies that the vector ABC this is equal to any free variable s 1, 0, 1. So finally, we see that the geometric multiplicity of this eigenvalue, so if we write here Gn is equal to 1. Geometric multiplicity is 1 because the dimension of the eigenspace that corresponds to the eigenvalue equal to 4, this is a single eigenvector. Then the big question is this: in order to have the A diagonalizable, how many eigenvectors were we looking for? Now, regarding the eigenvectors, here we have 1, here there is another 1, and these two correspond to the first eigenvalue. Here there is a third one. So apparently, the matrix that can diagonalize the matrix A, it can be written as follows. P, it's 1, 1, 0, which is this eigenvector here, minus 1, 0, 1, minus 1, 0, 1, and 1, 0, 1, 1, 0, 1. So this is the matrix that can diagonalize the matrix A, and we have P inverse times A times P is equal to what? This is going to be 2, 0, 0, 0, 2, 0, and the last value is 0, 0, 4. So this is how the matrix A will be diagonalized. And in the diagonal terms, these are the eigenvalues. Any question for what we had so far? Okay. Let's see a different example. So, given a matrix A, which is equal to 6, 2, 7, so let me ask you this question. So here we have a question. Given the matrix A, is 1, 1, 2 an eigenvector of the matrix A? Who can answer this? Any volunteer? You can raise your hand in the comment section. Joy wants to answer. Silvio? Silvio, Sergio? Okay, let's continue. So, Silvio, Sergio, Rubini. Rubini, I can pick the first one. Sorry, let me see here. So, or Lorena. Okay, Lorena. So you can answer this. So how can we check whether this 1, 1, 2 is an eigenvector? What can we do?
We simply multiply the vector by the matrix and see if their multiplication is a scalar multiple of the vector v.
That is good. So can you multiply them? What do we get? So let's multiply this 1 and 2. And what do we get? Can you do the calculation for me? So 6 plus 13 is 19 minus 8. What is this? 19 minus 8 is equal to what? 11. And the second value we get, no, it's wrong, sorry. This is, what is that?
19 minus 16 equal to 3.
This is 3, right? Okay.
Yes.
1. What is the second value?
Wait a second.
7 minus 4 is 3. And then we get 24. 24 minus 18 is equal to what? 6. So is this an eigenvector?
Yes, because 3 times the vector 1, 1, 2 equal to that one.
That's
So
correct.
the scalar multiple is 3. This shows that the vector we have is the eigenvector of the matrix given A.
That's true.
And the eigenvalue is 3. Yes.
That is correct. And then, so it looks like we found one eigenvalue. And can we find the other eigenvalues? So let's have a look actually. So we have lambda 1 times lambda 2 times 3 is equal to the determinant, right? And also lambda 1 plus lambda 2 plus 3, this is equal to the trace. What is the trace here? This is 11 minus 9, this is equal to 2. Okay, and what is the determinant? Can somebody calculate the determinant? Maybe you are faster at home. 6 times minus 45 plus 34, this is 11. 11 minus 13 times minus 18 plus 14 minus 4 minus 8 times 34. 34 minus 35 minus 1. Can you correct? Maybe I made some mistake. This is 66. 66 plus, what is this? Plus 52, plus 52, plus 8. This is huge. So we get something like 126. Am I correct? $126. Did we do a good job or we missed something? So this means that lambda 1 times lambda 2 is equal to 126 divided by 3, we get 42. So here we get 42. And then we have also that lambda 1 plus lambda 2 is equal to minus 1. So what is lambda 1 and lambda 2? Can we find these? I'm afraid we made some... can you calculate what is the determinant? A is equal to 613 minus 8, 6. Six, 13 minus 8, 2, 5 minus 2, and 7, 17 minus 9, 7, 17 minus 9. So here we have determinant of the little matrix A, this is minus 6. Okay, we made a mistake then on the board. Where was the mistake? So we said here 6 minus 13, this is minus 18, minus 8 plus 14 is minus 4, minus 18 minus 34. How is it possible? Is it?
I think it's the minus 11, the first one, not 11.
Is it? Oh, okay. Then this is minus 45 plus 34. Oh, this is minus 11. Okay, that's correct. Thanks for the notice. So this was equal to minus 6. So if this is equal to minus 6, the determinant divided by 3, this is minus 2. So if this is equal to minus 2, what is lambda 1 and lambda 2? We can do the following. We can have lambda 1 times, what is lambda 2? Lambda 2 is minus 1 minus lambda 1. Minus 1 minus lambda 1. So this is equal to minus 2. So here we have minus lambda 1 minus lambda 1 squared. This is equal to minus 2. Then we have lambda squared plus lambda plus minus 2. This is equal to 0. So this is equal to lambda minus 2, lambda minus 1. This is equal to 0. Then, at this point, so apparently, we were given an eigenvector, we found the eigenvalue, then given that eigenvalue, it made it easier for us to find the other two eigenvalues. So this means that we have another lambda 1, which is equal to 1, and we have a lambda 2, which is equal to minus 2. So now that we have these two eigenvalues, we can easily determine what are the respective eigenvectors. Okay, and you can continue the rest and see what we obtained. Oh, sorry, we are still, I'm afraid, we are still sharing the screen. Okay, do we have any question for this last example we covered?